So last time we were doing, what were we doing? Rational stuff. So I think we're doing polynomials over polynomials. We started with multiplying and dividing rationals. And we went to what? Adding and subtracting. We had to find a common denominator for the last homework. That was Maricheck 7.1 and 7.2. I think we are officially out of Maricheck now. I think everything else we're doing is out of Roxwald. And so 4.6, what were we doing in 4.6? We were talking a little bit about like what they look like graphically. We were talking about what their asymptotes look like, how to find their asymptotes. And I think I even like mentioned how to differentiate your whole from your asymptote, right? If it comes out, it's a whole. If not, it's an asymptote. Don't giggle. This is super serious stuff. So you got to be able to differentiate your whole from your asymptote, right? Determine whether f is a rational function and state its domain. Okay, so I want to go along here and just look at these things and like you kind of tell me whether they're rational or not. And if they're not rational, why are they not rational? Does number 1 look like something that's rational? Can y'all see that? Do I need to zoom in a little bit?
Yes.
Maybe I can focus it a little bit. Yeah, so that thing is rational. It is just a polynomial over a polynomial. Oh, that got blurrier. Don't do that. Why are you doing this to me? Now it's froze. It's just like really just like angry. There we go. That's a little bit better. So on top, it looks like x to the third minus 5x plus 1. That's a polynomial. 4x minus 5, that's a polynomial. This thing is a rational function. 6 over x squared, does that look like a rational function? And I know we're not supposed to do all these, but like we can look at them. It's not going to, it'll take you 1 second to tell me rational or not, hopefully. Number 2, is that rational?
Yes.
Yes, maybe the weird thing is like that 6, but we can think of constants as being a polynomial. They're just like x to the 0 power, maybe, if you really got to be silly. You can do x to the 0. X squared minus x minus 2. Is that thing a rational function? And we're expecting like to see a fraction here, right? But I don't see one, so what can I do? I can put it over 1. You can always put it over 1. And if I put it over 1, is that thing rational?
Yes.
Yeah, 1 is a constant. You can think of pretty much any polynomial out there as a rational function just being over 1. So it's kind of a silly thing to do because we would probably just look at it as a polynomial and not as a rational. But technically, under our definition, right, it follows the definition. What about number 4? So x squared plus 1 is definitely a polynomial. Is that rational or a rational function?
Not rational?
It's not rational, and just like to recap why it's not rational, because I have a square root. Square root are fractional powers, and so this goes back to the definition when we were talking about polynomials. Like all the powers in the polynomials have to be whole numbers, right? They have to be positive numbers. We're looking for positive whole numbers in our exponents. This is putting fractions in there. So anytime you see like a square root, it's not going to be a polynomial. Anytime we see something with a absolute value, is that a polynomial?
No.
That was not under the definition of our polynomial. 4 over x plus 1, is that a rational function?
Yes.
Yeah, it might be looking a little weird. If we really wanted to, we could probably write it as 1 is like an x over x. We could probably rewrite this thing as like 4 plus x over x if we really wanted to. But there's something on top, there's something on bottom. Don't let that +1 throw you off, I think is what they're trying to do. It is still rational. 3x over x squared plus 1. I think we've gone over enough of these, hopefully. But that's a polynomial, that's a polynomial. 8, I've kind of already said it. If it's got a absolute value, it's not going to be a polynomial. If it's got a square root, it is not going to be a polynomial. So I answered one question out of like 2 questions that they asked me, I think. Is it a polynomial? Or is it a rational function? It's a rational function if it is a polynomial over a polynomial. Now I want to state the domain. So the ones that I'm really doing, I don't want to do the domain for all of these. I'll jump to number 1 and number 9 are the ones I really should be doing. How do I find my domain on this thing? So I'm looking at number 1. What's the thing that's giving my domain? Or a better question yet is probably what can my domain not be? And how do I figure that out?
Take the expression in the denominator and set it equal to 0.
So we're taking the denominator and setting it equal to 0. We want to know what's going to make this denominator equal to 0. So what makes 4x minus 5 equal to 0? All right, so I'm hoping this is not the thing tripping you up. We've done plenty of these. So what makes 4x minus 5 equals 0? If we take x divided by 4, we get x is 5/4. So what is my domain on this thing?
Any real number as long as x doesn't equal 5/4.
So x 5/4 is the thing that I'm going to put. I suppose I could put all the rest of the stuff that we're going to take. But the main important thing here that we're getting away from here is that inequality x cannot be 5/4. Okay. Questions about this, about why we're choosing the domain. So this is that thou shalt not divide by 0, right? Like the first commandment of math. If the 4x minus 5 is 0, we've divided by 0, we cannot do this. So this is something we cannot have. We cannot have x being 5/4. The other thing is if you want to go plug in 5/4 back into this thing, right? Well, we're not finding solutions there. Never mind. That's the next section. I'm getting my wires crossed, I think. But if you go plug 5/4 back into this thing, right, it's not going to work because of this denominator. I guess we could still look at that part. Okay. And number 9. Number 9. We're looking at this thing. We've already said it's not a rational function, but I think we can still find domain or domain restrictions. If I want to find my domain restrictions, what restriction do I have? X squared plus x cannot be what?
Zero?
Yeah, and so I know I've been solving it with an equal sign. If you want to solve it with a not equal sign, that's fine. You can do that as well. Usually I do the equal sign until the end, but technically, I guess we could solve it with the not equal sign. So we know that x cannot be what? 0. We know that x plus 1 cannot be 0. And you're going to solve it just like you normally would with an equal sign, except you put a dash through it. So x cannot be 0. X cannot be minus 1. There really is something else I should account for in this one. We have a square root of x. So anytime you see a square root of x, this thing inside your square root has to be what? Greater than or equal to 0. So we can plug in a square root of 0. We cannot plug in negatives. We can plug in anything larger than a 0. So this thing in the square root is my x. So if my x is greater than or equal to 0, and x cannot be -1 and x cannot be 0, if I put these three things together, and it might be easy to do it like on a number line maybe if it's confusing. But I'm taking like everything greater than 0, and x is not a -1. I don't even have to think about this, right? This is like way over there. It's like, hey, I'm not this thing. Well, I know it because this one has to be greater than 0. And then if I put these two things together, x is greater than or equal to 0, but x cannot be 0. This makes x strictly greater than 0 is what your domain probably should be on this. I don't know what they did in the book or whether they even found the domain on this thing because it's not irrational. I didn't look in the back, if I'm being honest.
I think they did.
Did they do all that work?
Yeah.
Yeah, it's a lot of work and a lot of things to think about concept-wise when you're trying to introduce something new. But there you go. It might help to draw like a number line too, right? I got x. I got my 0 here. And one of my sets looks like this thing. Everything greater than 0. I'm going to take out, and I guess I'll take it out with an x. I'm going to take out that point, and I'm going to take out that point, right? I'm going to take out a -1, and I'm going to take out 0. And if I remove those 2 points, I'm going to end up with this thing with a hollow dot on the 0. I'm removing this point. I didn't have that point to begin with, right? I'm doing everything greater than 0. So that's a lot to combine in one problem, but they did it. But there's really two things to think about. One of them is we cannot divide by 0, right? That's where we're getting the two main restrictions that I really care about in this section. The other thing is that if we have a square root, it has to be greater than or equal to 0 for it to be a real number. And we talked about, I'm pretty sure we talked about this. Back when we did square roots. Square root of 0 is what? Do you remember these?
0.
Square root of 0 is 0. So we can take square root of 0. We can take square root of 1 as 1. We can take these, right? We talked about, I'm pretty sure we did. We did square roots a while back. A few nights. But we can do this, right? 2 zeros are going to give me a 0. 2 1s are going to give me 1 when I multiply them together. It's kind of silly, but it's a thing that's there. The thing we can't take square roots of, right, is negative numbers. This is going to give me i's. So I can't take this and stay in the real numbers, right? If I'm talking about the real numbers, this is giving me something not real. I got 9. Okay, this one, identify any horizontal and vertical asymptotes in the graph and state the domain of f. So I hope you can give me these equations by looking at a graph. If I'm looking along here, I'm getting the value of a what, -4 here. But what's the equation of this asymptote? What variable am I going to put there? Talk about that horizontal asymptote here.
Y?
That's going to be a y equal. Remember our y equals line look like things with zero slopes? They look like constant functions. This looks like a constant function of y equals a -4. So if I'm looking at this horizontal asymptote, that is a y equals a -4. This, I'm getting a value of what, 2 over here, and I'm getting a value of what, -2 over here. Guess what variable I'm going to put on this guy? The other one. The one that's not y. And that's happening at what? 2 and a -2. So x equals 2, x equals a -2. Okay, state the domain. So x is a real number such that what? What are my domain? What are my domain restrictions? Might be a better way to ask it, right? What can my domain not be?
Two or -2?
Yep. Okay, so I wrote the domain. I wrote it in what, set builder notation. If I wanted to write this in interval notation, I'm going from a -infinity and I'm going up to the -2, but I don't want to include it. And so just to give you like both of those sort of notations, I pick up from the other side of the -2. So this is kind of like how we skip over things in interval notation. I had to think of a second. This is set builder, this is interval. Okay, so this is sort of like how we skip over things. We go up to it, we don't include it, and we jump around it, and we go to the other side of it. So here I've just skipped -2. I want to skip +2. So I go up to it, I skip over it, and I go out to infinity. That is all real numbers except -2 and 2, written two different ways. Are there any questions about this guy? How to find asymptotes? So I think like if you got questions about it, definitely come see me. But I think visually, for the most part, I think most people get this. They see this asymptote visually. They know what the asymptote is. They can give me the equation y equals -4. Same thing with the x equals, right? They can give me the restrictions. Usually it's not going to go through my asymptote, right? It's never going to hit this value of a -2. It shoots off to infinity here. It shoots off to infinity here, and it never hits it. It gets really close, right? It gets really infinitesimally close to your asymptote, but it doesn't hit it. Okay, so this is what asymptotes look like graphically. I think we're going to have to find some asymptotes, horizontal and vertical. So we have already talked about horizontal. Well, no, we talked about domain. Sorry. But if we want to find horizontal asymptotes, what is the strategy to finding horizontal asymptotes? First, you should make sure it's fully factored. I think all these, 25 has a constant you can pull out, but for the most part, I think most of these are factored. 23 and 24 definitely are. Oh, we're doing 25, huh? Okay, we're not doing 23, 24. 25 is the one that we should be doing. So 25, if I want to find my asymptote, the first thing you should really do is make sure this thing is fully factored. So 4x is fully factored. What about 2x minus 6? Can I do anything with that?
Pull out the 2.
We can pull out 2, and that leaves me with what? X minus 3. If I wanted to, and I don't really think you could probably get by with not doing it here, if I'm being honest. I think you could probably still find the asymptote on this one without simplifying it. Because 2 is never going to be 0. I could simplify this a little bit. So how am I going to simplify this? What simplifies here? How does it simplify?
Two and 4.
Yeah, the 2 and the 4, I can divide both of those by 2. If I divide both of those by 2, this becomes 2x over like x minus 3. And how do I find my horizontal asymptotes? So the first step is to fully simplify these things. First thing is to fully simplify these things, and then the next step is to see what is what. So we know they're going to be domain restrictions. We found domain previously. How do we find our domain?
Are we still on 25?
Set the denominator equal to 0.
Yeah, so this is exactly, we're doing the same thing, except we simplify first, right? So if we want to know our domain restrictions, we set the denominator equal to 0. If we want to know horizontal asymptotes, we simplify and then set the denominator equal to 0. So you do have to simplify this thing first. This one, it probably doesn't matter, but certain problems it will matter. So x equals 3 is what I'm getting. And this should be my horizontal asymptote.
Wouldn't that be the vertical?
That would be vertical. That's absolutely vertical. Sorry. I get vertical and horizontal mixed up really bad. I got to think about it, and I was not thinking about it at all before I said the word there. So that is definitely vertical. It is going up and down. Okay. So we found vertical asymptote. The next thing we want to find is what? Horizontal asymptote. So the vertical asymptote, I think, is probably the easier one to find. We simplify it and we set the denominator equal to 0, and that gives us our vertical asymptote. The horizontal asymptote, it had some rules to it. So do you remember, you probably, maybe you do or don't remember the rules, but like, what do we look for? What are we looking at when we look for a horizontal asymptote? So we're looking at both the polynomials, and what about those polynomials do we look at?
We want the y value.
We want the y value, yes, but we're looking here. And so what are we looking at on these polynomials? There's something we should really be looking at.
The exponents.
The exponents. So this is a first exponent. This is a degree 1. This is a degree 1. And so you might notice this is the same degree. So same degree had a rule. Larger on top, smaller on bottom had a different rule. Smaller over larger, right? So we're looking at the degree of this thing and just sort of like quick recap of the rules. If it's the same, we have this rule, it's like A over B, it's the leading coefficients. That's what we're about to do in a second, so I'll talk more about it when we finish that problem. But let's look at, they're not the same. If I have a smaller degree over a larger degree, so as this thing is going off to infinity, this thing is getting larger and larger relative to this thing. So this is kind of like you have 1 over like a really, really large number, like 1 over a million, or 1 over a billion, or 1 over a trillion. What is this going towards? If I keep getting larger and larger on the bottom, like 1 over 10, right? If I go 1 over 10, 1 over 100, is that a weird question to ask? What's happening to this number? Like 1 over 10, 1 over 15, right? 1 over what? What happens if I get larger and larger on the bottom? What number does this go towards?
Infinity?
The bottom's going towards infinity. That's what I'm saying. But if I do like 1 over a number, right? If I do 1 over a number, like 1 over x, we've looked at this graph too, right? What is this thing going towards? Let's probably zoom in a little bit. But I do 1 over 1, it's going to give me 1. I got 1 in there. And I keep going, right? What is this line going towards? Like over here, way, way on the right. Can I scroll past? No.
0.
It goes towards 0, right? This goes towards 0. So what this is going to give me is something that looks like y equals 0. So if I have a smaller power on top than I have on bottom, I'm going to get y equals 0. It's going to go towards 0. This is a sort of like you're thinking about 1 over a really large number, right? And I know this is really horrible notation, but I'm going to put it there. It's like 1 over infinity, 1 over going towards infinity. That thing is going to go towards 0. The larger the number on the bottom gets, the smaller the number overall gets, right? Oh man. Yeah, people don't grasp that all the well intuitively all the time. There's an example where A&W came out with a 3rd-pound burger and they charged less than a 1/4-pound burger, but it did not do so hot. People aren't always that great with fractions. So 1/4 is smaller than 1/3, just so we're all on the same page. The larger the number on bottom, the smaller this number gets overall. So vice versa, if we get something very large on top, this is sort of like thinking about we're shooting off to infinity here and we remain that on the bottom. There's not a lot we can say. No horizontal asymptote here. And so these were the 3 sort of rules. I'm looking at the exponent on my numerator. I'm looking at the exponent on my denominator. If they are the same, I do leading coefficients. Something like A over B is, I think, is what they said in the notes, maybe. If it's larger on top, that really doesn't tell me anything about it. There's no horizontal asymptote happening there. It's not leveling out. It keeps increasing as it goes off. Or it decreases, one or the other. Could be the other way. But there's no sort of consistent thing happening. If we're getting really, really large on bottom, that's sort of like this thing is going towards 0. So we get a horizontal asymptote of y equals 0. So we have to think which one of these 3 does this rule fit? If we look at this, this is the same power. So we notice this is the first power, this is the first power. So what is the rule here? I want to take my coefficients. So what are my coefficients here?
4 and 2.
The 4 and the 2. So what I'm going to do is I'm going to look at my coefficients on the leading degree. I see 4 over 2. So this should have a horizontal asymptote at 4 over 2. It should be y equals 4 over 2. So this should have a horizontal asymptote at y equals 2. So what does that look like? X button stuck. Okay. So if you want, it might help you out a little bit if we go look at this on what, Desmos? So we said x equals what? 3 was the one? Looks like. Y'all see the x equals 3? Right here. It looks like an asymptote here, hopefully. We can check these things, hopefully. Y equals 2 should be my other asymptote. Does that look like the right place? That looks good, huh? So we're starting symbolically and we're finding asymptotes off of this thing. If they wanted us to graph them, the first thing we would probably graph is our asymptotes, and then we would probably graph the shape of this thing. So we did a few like those in the notes. You'll probably do a few more of those. Where is my little bar? Where'd my bar go? There it is. Trying to find my annotation bar. Okay. 25, the next one we want to do is 33. And 41 are the next two. Okay, so I want you to go ahead and find vertical asymptotes. I want you to attempt to find vertical asymptotes on both of these things, and then we will go through and find horizontal asymptotes. And so as a reminder, if it's not fully simplified, the first step to finding your asymptotes is to make sure that thing is fully simplified. Okay, so if you want to find the first one, how do we find the vertical asymptote on 33?
X squared minus 5 equals 0.
Yeah, so 3 over x squared minus 5 is already fully simplified. So what we want to do is we want to take the denominator, we want to set it equal to 0. So x squared minus 5 equals 0 is what we have now. Oh man, if you didn't think factoring was going to come up, what did I tell you? Look over there. We're going to have to know how to factor these things. What's the easiest way to factor this, or the easiest way to solve? Someone said something. I didn't hear what y'all said. We had x squared minus 5 equals 0. What's the easiest way to solve this one? What's process?
Square root property.
Square root property. So add the 5 to the other side. Someone got? Okay. We take the square root, and when we take the square root, when we take the square root, we have to take plus or minus when we take the square root. So that was a square root property. I put an approximation in here. Okay, so if we go and we graph this thing, it should have asymptotes at what? X equals 5. Let me copy and paste this. Control C. Should have roots at, or asymptotes at root 5 and negative root 5. And so if you want to see a picture, here's, let me throw up Desmos right quick. This is sort of what our picture is looking like. We have asymptotes at root 5 and root negative 5. That's somewhere around like 2.23 in there or something if you want to approximate it. So hopefully you can see how those look like they're asymptotes. Those are getting from the bottom. The other thing we have, the next problem, where am I at? Stop. Looks like x squared, where is it? Minus 9 over x plus 3. How do we find the asymptotes on this thing? And this one is a little bit different because what should we really do first at this? If you don't do it, you found something, but you didn't find what you thought you found. So if you tell me x equals a minus 3, this is a domain restriction, right? So if you would be correct in finding that this is a domain restriction. But what should we do to this first? If you see x squared minus 9, what can we do with that?
Difference with squares.
We can do a difference of squares. And if we do a difference of squares, I've said it, like if we do this and we want to find the asymptote, the first step is to make sure these things are fully simplified. So if it's not fully factored, we have to factor it. We have to see and make sure these things are simplified. So if we simplify this thing, what am I getting out of this thing? It looks like my x plus 3 should simplify. I should emphasize that's the vertical asymptote. What's my vertical asymptote on this thing then? And maybe it's a bit of a trick question.
Y equals minus 3.
What? I didn't catch that. What should my asymptote on this thing be? What's down here? Just a 1 maybe, if you want to put it. So when is that going to be 0?
Never.
Never. So there are none, right? There's no vertical asymptotes on this thing. So what does this thing look like? It looks like the graph of x minus 3. What does the graph of x minus 3 look like? What sort of graph is that?
It's a straight line. It goes,
It's a straight line.
what is it, like horizontal?
Yeah, so it looks like, no, not horizontal, but it goes
Oh, vertical.
like x plus 3, right? X plus 3 is it?
Okay, sorry. I was thinking y.
No, x minus 3, sorry, is what we're left over with. It's just the line x minus 3, basically, right?
Yeah, because it has a rise over 1. Overrun is 1 over 1. I forgot about that.
But we got this thing where x cannot be 3, right? Or minus 3, sorry. So what's happening at minus 3?
There's a hole.
There's a hole. There's a hole in the middle of the graph. There's a hole in the middle of the graph. Where is it at? Right there. You see it? It looks like a circle that's not filled in when I get right over the 3. There's a hole in this graph at a minus 3. So we see this x plus 3 and we're thinking, hey, there's like a domain restriction there, but it simplifies out. So if it simplifies out, it is a hole. So we still can't plug in x equals a minus 3, right? But we basically have the graph of x minus 3 without without x equals minus 3, right? Is what's happening. And it doesn't understand all that, but whatever. So that's basically what we have. We have the graph y equals x minus 3 without this thing in there because this thing is a hole. There are no vertical asymptotes. Now we want to go look and let's stop this. Let's compare and contrast. Let's go and look at all three of these at once, sort of, and let's just get the horizontal asymptotes on all of them. I think that's the best thing to do. So going back to this thing. And we got 3 over x squared minus 5. And we got another one that looks like y equals x squared minus 9 over x plus 3. So not even simplifying them. I just want to find my horizontal asymptote. We talked about this guy. If they are the same, what we do is we look at the leading coefficients. And y equals 4 over 2 or y equals 2. So we did this one already. If I'm looking here, what do these two look like now? If I'm looking at the powers, is it larger on top or on bottom? Is the question I'm asking.
On the bottom.
This is larger on the bottom. This is the other way around, right? They're trying to give you kind of like one example of each thing happening here. So if it's larger on bottom and smaller on top, so you can put numbers in here if you really wanted to, right? You could go in your calculator, you could plug this in 3 over x squared minus 5. But if we think about like putting in 10, we're gonna get 95 on bottom. If we put in 100, it's gonna be like 9, 9, and 5 or something, right? It's gonna get really, really large on bottom. This top is gonna stay 3 no matter what. So this is kind of like it's going towards what number? And this is that it's like 1 over a really large number.
Zero?
Yes, this is the one that's going towards 0. So y equals 0 is what this thing is going towards. So if you get something really large on bottom and something really small on top, it's going towards 0. If we get something large on top and small on bottom, you could probably just do this sort of deductively. Like this, we get the a over b. This is the 0. This one is what? What can we say about this? And maybe that's a bit of a misleading question. Because there's not a lot we can say about this, right? So if we get something that's larger on top, what is my horizontal asymptote? What would you tell me, I guess, is a better question.
There is no asymptote.
There is no horizontal asymptote. And these are the 3 sorts of scenarios you got to look at. We're just looking at the power on our polynomials that are in our numerator and in our denominator. After we look at the powers, what? Oh, do you have something?
I just want to make one comment too. Sometimes, and I know I saw this, I'm not sure where I saw it, maybe on the written assignment. They might have something like x plus 2 times x plus 3 already factored or over something, and they need to, I guess, know what happens. You know, they have to multiply it out in order to see the power on the top, or at least think about it.
Yeah, so they give it to you in factored form, like x plus 1, 2x plus 3. Same thing on bottom or something?
Yeah, something like that.
Right. We would still have to be able to do some distribution. So you do want to put these in like expanded descending order to know what your horizontal asymptote is. So they have them already kind of here in descending order, and they're fully expanded, right? If they give them to you in factored form, we're going to have to do some distribution. So something like 2x squared plus what, 6, 3x. Let's see if I can still do distribution. Plus 2x plus 3. And we do something like 3x squared here, plus x, minus 6x, minus 2. And I really should combine my terms, but I'm going to be really lazy. Well, I'll do it. 2x squared plus 5x plus 3 on top. We really don't have to combine the terms, because if we look here, what I'm really concerned with is what is the largest degree? The largest degree here is 2. It is the same degree top and bottom. So if I wanted to know my horizontal asymptote on something like this, don't forget your y equals, but it should be the line y equals 2 over 3. So these, when they're the same, the way to think about it is they're increasing or decreasing at about the same rate. And so the thing that really comes into play here is what are they being multiplied by? What is that coefficient that is on them? So when you're going out to infinity, right, it's the larger power that really kind of dictates things. These things kind of get dwarfed by this guy out here when you talk about really, really large numbers. So if they're the same power, it's the coefficients. If it is smaller on top, larger on bottom, that's the thing that's kind of like it's going towards 0. This is the thing like you should probably think of like 1 over x, right? As x goes to infinity. I'm giving you some notation that's beyond this class. But you're thinking about that 1 over x as your x is going off to infinity. 1 over a really large number looks like it's going towards 0. If it's a larger thing on top and smaller on bottom, we can't really say anything. It's shooting off towards infinity or something crazy. Was that 41? 43 through 46. We got like 2 more. Okay. So these, they want us to match them with A, B, C, D. Okay, so what are some defining features? We probably want to know what vertical asymptote, we probably want to know what horizontal asymptote. Find it. So if I'm looking at 43, what would my vertical asymptote be on 43?
One.
Yeah, so x equals 1. When x is 1, that denominator is going to be 0. A is just some kind of coefficient, so or some kind of constant. They're not telling us what A is. I believe it's just a constant in these problems. So we know it's got a vertical asymptote at x equals 1. Does it have a horizontal asymptote? So what is the numerator or denominator a larger power is the first thing we're asking.
Neither.
This is a first power. If this is a constant, what power can we think of constants to?
0, so the bottom's bigger.
0. So the bottom is greater. So this should have a y equals. If it's larger on bottom, this is like the bottom's getting really, really large compared to the top. This is the y equals
0.
0 thing that I've been talking about. If I think about 44, my vertical asymptote, my horizontal asymptote, I want to find those two things. Do I have a vertical asymptote here? I don't want to spend a lot of time. But it's exactly the same as the previous problem, right? X equals 1. It is the same denominator. It is the same vertical asymptote. What about my horizontal asymptote? Do I have a horizontal asymptote here? What is the degree of these polynomials? Are they the same? Are they one larger? Is one smaller?
Same degree?
They are the same degree. This is to the first degree. This is to the first degree. So if they are to the first degree, if they are to the same degree, what's the rule? We take the what?
Leading coefficients and divide them?
We take the leading coefficients and divide them. There is a 2 here. I don't see it here, but if I wanted to, I could put a 1 in front of that. This should look like y equals 2 divided by 1, or we could just say 2. So with these two things, I think we might have enough information to probably maybe get these two out there. Let's see. X equals 1. So x equals 1 is one of my asymptotes. It looks like, are these? Well, this one gives me x equals 1 and y equals 0, so that might be one of them. Let's see. So if I'm looking at these, I know x equals 1 is the same, y equals 2. X equals 0. X equals 1. X equals. This looks like. So I know I'm probably going a little fast, but I hope like usually graphically y'all can get these things really quick. So if I'm going too quick, yell at me, scream at me, be nice about it. Definitely tell me something if I'm going too quick with finding these asymptotes graphically. But if we start labeling our asymptotes on the graph, I think that will get us what function matches which pretty quick. So I think right away, I think A is going to only match 44. I think that's the only one that has asymptotes at x equals 1 and y equals 2. B has an x equals 1, y equals 0. This one has an x equals minus 1, x equals 1, and y equals 0. So we know 43 has an asymptote at what? X equals 1 and y equals 0. Does it have a vertical asymptote at minus 1? This thing?
No.
No, it's only got one vertical asymptote at x equals 1. It's got a horizontal asymptote at y equals 0. So I think that deduces this thing down to B. So there was only one thing that matched the conditions of this thing, a vertical asymptote at 1 and a horizontal asymptote at 2. Make sure I get those words correct. Like I said, I have a really bad habit of reversing horizontal and vertical when I say them. So with that said, I think these are the only two that match those two and the things that we just found about them. If we want to find the next thing, what is my vertical asymptote on 45? So if I want to find my vertical asymptote, what am I doing to 45?
X plus 2 equals 0.
We said x plus 2 equal to 0. And so if I solve that, I should be getting x equals a minus 2 for my vertical asymptote. If I want to know my horizontal asymptote, does this one even have a horizontal asymptote? And if so, what is it? So I'm looking at the degree of the function on top. I'm looking at the degree of the function on bottom. What do you notice about this function?
Same.
They are the same degree. And if they're the same degree, what is this sort of rule that I do? I look at where?
The leading coefficient.
The leading coefficients, and you might notice your leading coefficients here are both 1. So I'm sorry, what?
So it's y equals 1?
Exactly. It's y equals 1 over 1, or y equals 1 is my horizontal asymptote here. And the last but not least, if I find my vertical asymptote and my horizontal asymptote, you could probably use the power of deduction without doing this last one. Ooh. But if I wanted to figure this out, I would set what? X squared minus a equals to 0. Yeesh. I guess we could do that. X squared minus a equals 0. We're going to add the a over and take its square root. We would have to use the square root property. So we did something very similar in our notes. But we did it with the number earlier. I think we did it with the number 5. But there would be 2 vertical asymptotes on this thing, is what they want you to notice. And then the horizontal asymptote, ooh, that's a good question. What is my horizontal asymptote on this thing? So if I'm looking at the powers here, I don't see it. I can put 1. Which one is, are they the same? Are they larger?
Larger on bottom.
Larger on bottom. If it's larger on bottom, what does that mean about my horizontal asymptote? Does it have one? Or does it not?
It does?
It does. It absolutely does. And it is y equals
0.
ooh, so yes, that's it. Good. It's like that little degree of uncertainty, but I can hear you getting it. It's clicking, I think. First time seeing it, probably, huh? A lot of stuff to remember. This is a heavy chapter, concept-wise, right? It's like I got to remember these 3 rules just for horizontal asymptote. What are they trying to make me do? But I think we have enough information to fill out everything else. So 45 had x equals a minus 2 and y equals 1. I think that would give me D and C. So bad C is what this is. Does that seem correct to y'all? Any objections? All right, so we got a few more. I think there's just 2. No, there's 1 more and 2 word problems, I think, is what's happening. Write a formula for f of x for irrational function so that its graph has a specified asymptotes. Oh, man. So this is a little bit weird and backwards. But we can work with it. So vertical, if we're going to get x equals a minus 3, what is this telling me? Where is this coming from? This is the thing that came from the denominator, right? So how do we back solve this, I guess is the question. If we got x equals a minus 3, what does that mean was in our denominator?
X plus 3.
X plus 3. So this is like looking at x plus 0. If we were to solve this, we would get x equals a minus 3. So this is sort of like going backwards, sort of like when I did factors. Hush. Yep. So this should be in my denominator is what this is sort of telling me. So I have something. I have something that looks like x plus 3 in my denominator. I want y equals 1 in my asymptote. And so if I'm getting y equals 1, well, if it's larger on top than it is on bottom, I'm not going to get an asymptote. So that's not the case. If it's larger on bottom, it's going to be 0. So that's not the case. So what this is telling me is that these had to be the same degree. I think that's what this is telling me. So what should I put on top? This is x to the first. What do I need to put on top?
X.
I need to put an x to the first power on top as well. And is this fitting what they told me? Can we check this and see if it fits? Would this have a vertical asymptote at x equals a -3?
Yes.
Yeah. Would it have a horizontal asymptote at y equals 1? And if you got to think about it, 1 over 1, it should, right? Could we write something that's crazier? We absolutely could. There are crazier things. We could start tacking on more terms here if we wanted to. This is what they asked for. This is probably just as simple. This is probably as simple as it gets, right? We could definitely make it more complicated. Are there any questions about this? If I'm being honest, this is a really good homework question. I'm not so sure that this would be a test question, if I'm being honest. I have to go look back at what Miss Watson did for a test. I skimmed it over. It looked pretty good. But it was a really quick skim this morning. I didn't really look.
Yeah, there is an application problem where they are asked to interpret what's happening with an asymptotes.
But not
Yes.
finding a formula, like back solving for a formula.
No.
This is a little bit weird. It makes
Not 47. No, right. No.
yeah. But these application problems, these ones, 121 and 125, these are definitely things you should look at. There are definitely things that could come up.
And they're good to know. I mean,
Yeah, I mean, asymptotes, they exist in reality, right? That's why we're sort of talking about them.
and they exist. Like if you take a business math course or something, you'll see these kinds of problems for sure. So.
Okay, so 121, if 2 parking attendants can wait on 8 vehicles per minute and the vehicles are leaving the parking garage randomly at an average rate of X vehicles per minute, then the average time T in minutes spent waiting in line and paying the attendant is given by this formula. T of Z equals, oh man, -1. Oh, that's T of X equals a -1 over X minus 8. So maybe let me rewrite this a little bit. It's written right there too. This is my formula. You might notice they do a little bit of bounding with their domain there between 0 and 8. So we can't talk about anything less than 0 cars per minute. So X is my traffic rate in cars per minute. And then T is going to be my wait time. So they ask us to evaluate T of 4 and T of 7.5. So T of 4, what does that look like? We've done quite a few of these things. We're plugging in 4 for X. We've done function notation before. Now we're just doing rational functions, but it's the same concept, right? The 4 takes place of the X. The 4 takes place of the X. So what is T of 4 giving me? I think it's giving me minus here. 4 minus 8 is going to give me -4. This is giving me a positive 1/4, 0.2. And I think it's probably maybe be easier to be 0.25 minutes. So they want a little bit of interpretation. So X was the rate that cars arrived. So what rate are cars arriving? I think they're doing 4 cars per minute. So if cars arrive at 4 cars per minute, the wait time is 0.25 minutes. Is what this thing is telling me. If we look at our graph, does that match up with what we're probably seeing on our graph? Does 4 look like it's going through about 0.25? It looks about correct. What about 7.5? Now I want to plug in 7.5. What's going to happen to this graph?
I say that'll go to approximately 1.25 or something. That's what I think.
This is 1 divided by a half. Or negative over negative, this is positive, but this is 1 divided by a half, and we talked a little bit about this. But 1 dividing by a half is the same thing as 1 multiplying by 2 over 1. This is giving me 2.
Okay. So it's bigger than the last one.
2 minutes. Yeah, I really should interpret this and go back and interpret this, but I'm being kind of lazy, I guess. If cars arrive at, what, 7.5 cars per minute? I guess I'll do some interpretation. Half English here. If cars arrive at 7.5 cars per minute, wait time is. So what happens if we do 7.9? How long are we waiting? I think it's 10 minutes then, right? We do 7.99, how long are we waiting? 100 minutes, I think. So they want you to keep plugging stuff in. Evaluate these two and interpret each result. What happens if the vehicle arrives? Let me get it. Okay. It's hard to read on that. Trying to read it on my screen and it didn't work. What happens if the truly wait as vehicles arrive at an average rate that approaches 9 cars per minute?
8 cars.
Did I say something weird?
You said 9.
8 cars per minute. Yeah. A negative 1 over x minus 8. Let me make sure. Not you. Make sure I get it in my calculator right. So I think you do need parentheses around the denominator. I could be wrong. But negative 1 over x minus 8. And I talked a little bit about this, but variables function. You can actually pull this thing up and you can look at what? 4 should give us 0.25. We figured that out already. 7.5. If you want to go to your table, that's another way you could do this. But I want to think about just like getting closer and closer to 8 here, right? 7.9, right? Is it going to give me 10? 7.99. 7.99999. What's happening as I get closer and closer? What do you notice about this? What's happening to my wait time?
The time is increasing like by a factor.
It's increasing dramatically, right?
Dramatically.
Even if I go like 0.009 more, right? This is going like 1,000 times more or something. I'm not increasing my x very much, but my y is just blowing up, right? Do we see that graphically happening here? And what does that tell me?
It's not a straight line. It's not the same all the way through.
Yeah, they're telling me it looks like this. It's going up. It's blowing off to infinity is what's happening, right? So are we going to ever hit 8? What happens when we hit 8 cars per minute? Can we hit 8 in this scenario?
No.
No, it is a asymptote here, is what is happening. So this thing is shooting off to infinity as we approach 8. What that indicates is that this is an asymptote. Infinity, right? Towards infinity. Is there any specific verbiage you're looking for there? Anything that you might want, Ms. Watson? I think that's probably pretty much it, right? Just shoots off and towards infinity really quick. That's what the asymptote does. It's never going to hit it. It's just going to go shoot off to infinity, like completely avoid it. Do its best it can to avoid it, right? How close does it get? Infinitesimally close, right? We go up to 7.999999999, right? As close as you can believe. but it never quite hits it. But the closer and closer we get, the quicker and quicker it goes up, sort of thing. Any questions about this? So like horizontal asymptotes, they look like they're kind of like a limit here, right? There's like 2 people working this thing. They can wait on 8 vehicles per minute. That's as fast as these like 2 people can work, right? You start getting more vehicles in there per minute over 8 vehicles, you're going to get vehicles stacking up is what this thing is telling me. Like vehicles are going to stack up real quick. And the closer we get to 8, the quicker they're going to start stacking up, right? Is that making some sense? They're yes. Trying to get you to take this concept of like asymptotes, and they're trying to get you to apply it to something in reality, right? And so horizontal asymptotes look like things that we can't reach. They're going to be sort of limits, is what's happening basically. Suppose that an insect population millions is modeled by this thing. We got 10x plus 1 over x plus 1. Okay, so they didn't ask for it, but if they wanted a vertical asymptote on this thing, x cannot be a minus 1. That doesn't even really like come into play here, because x equals a minus 1 isn't even in our domain. So they don't ask it at all here, but if they did ask for a vertical asymptote, it wouldn't even really matter too much on this equation because it's beyond our model, so to speak, right? We want to determine the initial insect population. So how do we determine the initial insect population? X is the number of months and f of x is our insect population. So initial population is like saying when our time is what?
0.
0, so we plug in 0 to which thing?
X values.
Hopefully, because we hadn't done the other way around yet. We plug in 0. What number is that giving me? I think it's 1 over 1. I think it's giving me 1. So there wasn't no, there wasn't one insect. There was one insect population. What they're talking about is the population in millions, I believe, or something here. Yes, population in millions. So this means there were 1 million insects initially. Oh man. Plague of locusts, that's all we need. That's the next thing, right? What happens to the population over time? Interpret the horizontal asymptote.
Did you graph it on the calculator?
I did not graph this thing yet. I should probably graph it for them, right?
Well, part A.
Part A does say graph it on a calculator, huh?
Yeah.
We weren't supposed to do part A. They said kick that thing off, but
well, why would they do that if we can't see? Well, never mind.
Yeah, okay. You might be able to kind of interpret like 10x plus 1.
Yeah.
It's probably going to be a little bit larger than x plus 1, right? But not a whole lot. So let's go ahead and graph this thing. It's so quiet. I don't know. My AC just kicked off and it's just like.
Can you hear me?
Yeah, it went from that AC hum to nothing really quick.
Can anybody hear me?
Yeah, I can hear you.
Oh, okay.
It just went eerily quiet. Y'all can see this, right? Okay, yeah, I'm sharing. So this is the 10x plus 1 over the x plus 1. And we hadn't talked about it, but if I wanted to do a horizontal asymptote, what do you notice about the powers of these two things? Are they the same? Are they different? Is one larger than the other?
The same.
You mean?
They are the same. So this has an asymptote at y equals what?
0.
That would be
they're the same?
That would be if the bottom's larger, it would be y equals 0.
Oh, so they're the same. It equals
10? 10. 10 over 1? Or we just do y equals 10?
what is it? Oh.
And if we look along here, do you see why that's an asymptote? As we go off, right? This thing is not going to pick above 10. So what is that telling me? What happens to the population over time? Well, if we look at it, it's going up really dramatically right here, right? It's going up really steep. And then what starts happening? Starts getting less steep here, right? And less steep and less steep. So the population is increasing less and less as we go on. Sort of like it's overpopulating or something. So why is that happening? Like realistically, pulling in like the knowledge you know about like, you know, ecosystems and that sort of thing. What is happening with the horizontal asymptote?
The population is sustainable until 10 million.
Population, right? Like there's a limited amount of resources. You're only going to populate so much before you start overpopulating, right? They call this, I believe this is called the logistic model. They do this in the other class.
Yeah.
And they call this thing a logistic model. There is a way if you come along here and you overshoot, if you overshoot what you're going to have, there's usually a crash. So there's an overshoot and crash model that they kind of juxtapose with the logistic model. So the logistic model picks up, and this is ideal population growth, right? Is what they're kind of showing us. Ideally, your population picks up, and as you get close to how much you can sustain, you quit populating so much, right? You don't want to overshoot. That's a bad thing. When you overshoot, there's usually a collapse that follows, which means your population jumps down, right? Which means people are dying like crazy. It's just not the ideal scenario, right? So what happens to the population over time? We answer that. It goes up, and it goes up at a slower rate as we go on. Any questions about this thing, about what they're getting at here? Okay, that's the last one we got. I think we're 5 minutes over now, actually. I think we can hit stop on the record if you haven't got questions.